everyone. Today we are going to continue exploring quadratic graphs, but today we're going to talk about what the graph of y equals ax squared plus bx plus c will look like where a is less than 0. Numbers that are less than 0 are negative. So we're specifically looking at negative values for a, the coefficient in front of x squared. So first off, we are going to look at how a negative a value will change your quadratic graph. As always, we're going to start off with our generic y equals x squared, and we're going to compare it to now y equals negative x squared. So if you remember, our table of values looked like this for y equals x squared. So while you're making your prediction for what y equals negative x squared will look like, you might want to consider how your y values will change now. So go ahead and make your prediction. And then we're going to hop on over to Desmos to see if your prediction was correct. Okay, so we have the graph for y equals x squared, and we need to compare it to y equals negative x squared. So the y equals x squared is in green. It's a parabola opening upwards. Let's see what happens with negative. Oh, look at that. Now it basically flipped over the x-axis, and now instead of opening upwards, it's opening downwards. It changed the direction. Back in my notebook, I'm going to go ahead and draw a sketch of each of these graphs. My original y equals x squared is going to open upwards, and then in comparison, my y equals negative x squared, everything else is the same except it's opening downwards. Now we're going to look at our table to see how come that is. Well, we have a negative in the front. That negative is going to be added on at the end after we square our x. Okay, so this is very different compared to the negative being attached to the x. This negative is not attached to the x, so it's basically just going to change your final answer into a negative. Here, if it were inside the parentheses, it would change the x value to the opposite sign and then take that answer and square it. Okay, so this negative is not acting with the x, but instead tagged on at the end. So these values just become negative. And then so that's why your graph ends up being flipped, because now instead of being up here in quadrants 1 and 2 with all positive answers or values for y, they're all going to be negative. So that's why everything is flipped over. Okay, so make sure you add that into your notes, that your parabola opens downward because y values are all negative now. Okay, so that negative sign gets tagged on at the very end. Okay, let's take a look at another problem to explore. This one says to predict the graph for y equals negative 3x squared. Go ahead and try and make a prediction first before we hop on over to Desmos. What would that graph look like? Okay, let's see what happens with your graph of y equals negative 3x squared compared to your y equals x squared graph. Okay, since it was a negative a value, it's now opening downwards, your parabola. And since there was a big number, like 3 being multiplied by x squared, it became a more narrow parabola. All right, let's go ahead and sketch what that would look like. Normally it would be opening upward. This one's opening downwards, and it was very narrow because of that 3 that was being multiplied. So it opens downwards, and narrow. Okay, now we have another graph to predict. This one says to predict the graph for y equals negative x squared minus 2. Make your prediction. What would that graph look like before we graph it on Desmos? Let's see what the graph for y equals negative x squared minus 2 will look like compared to our y equals x squared graph. Opening downwards because it's a negative value for your a. Same shape or width as your original x squared. And then since we had a c value that was minus 2, it shifted down 2 units on the y-axis. Okay, let's sketch what that result was. It was opening downwards and it moved down 2 units. Wasn't any particular width because there wasn't a number other than the 1. So let's go ahead and write down that it opens downward and moved down 2 units. Okay, and then lastly, we want you to predict the graph for y equals the negative quantity of x plus 1 squared. So keep in mind this one has a negative outside. So it's going to be a negative value that's tagged on to your final answer, and then plus 2. And then in simplified form, it's negative x squared minus 2x plus 1. So make your prediction before we head over to Desmos to check and see if you're correct. Okay, the graph for y equals the negative value of the quantity of x plus 1 squared plus 2. It is opening downwards because of that negative. Because of the plus 2 at the end, it's going up 2 units on the y-axis. And then because of the plus 1 with your x value, it's going to shift to the left 1 unit. So to the left 1 unit because of this plus 1, and then going up 2 units because of this plus 2, and then opening downwards because of that negative sign. All right, we're going to sketch what our graph looked like. It was opening downwards. It had shifted to the left 1 unit and then up 2 units. To the left 1 unit, up 2 units. So this was its center right here. Okay, so opens downwards. Let's see, left 1 unit and up 2 units. So that's all you need to know now for your characteristics of quadratic graphs. Depending on what your equation looks like, you can tell what direction it opens, how many units it's going left and right, up or down from the origin. All right, so let's go ahead then and look at an example from the book. Here's example 5. When a stone is thrown upwards from the top of a building, notice how the stone makes the shape of a parabola. Its height h meters from the ground at time t seconds is given by h equals negative 5t squared plus 10t plus 40. And this quadratic equation is used a lot of times in physics, which is a science where they're looking at objects in motion. So if you're into engineering, you're going to see this equation so much in the future. All right, A wants us to draw the graph of that equation for just the values of t that are equal to or greater than 0, equal to or less than 4.5. Find the height of the building, which we can do, and find the time of flight of the stone. We can also figure out when the stone is 20 meters from the ground. And then they also want the line of symmetry for the graph and the maximum height of the stone from the ground. So again, this equation is used a lot, this quadratic equation in physics, because we can figure out all sorts of characteristics of a moving object with a quadratic equation. Go ahead and pause the video and try it on your own first. All right, so we are going to, again, just look at the first quadrant for our graph, because we are not dealing with negative values for height or for time. So just need this section of the graph that deals with positive numbers. And we're going to go ahead and graph this. Okay, first off, I'm going to need to draw a table. Instead of x and y, I have t and h. I know that t is basically like x and h is basically like y, because usually it's y equals something times x squared, right? So it's just substituting other variables instead. I'm going to figure out my values for 0, 1, 2, 3, and 4, okay? Because they want values between 0 and 4.5. Okay, so if if t were equal to 0, it would become -5 times 0 squared plus 10 times 0 plus 40. Well, both of these will cancel out because anything times 0 is 0, plus 40 at the end, so the answer is 40 for h. Next up, if t were equal to 1, I'll just replace my t with 1 to solve that. 1 times 1 is 1. 1 times -5 is -5. -5 plus 10 plus 40. So this is really -5 plus 50, which is 45. And then let's see, let me give myself some more space. So now I'm going to replace t with 2. Okay. And here I will need to figure out all the values because it's not a constant rate of change. So I can't just connect my 2 points and make a line because I know it's not going to be a straight line. I need to figure out how it curves. Okay, so here is -5 times 2, which is 4, plus 10 times 2 is 20, plus 40. So this is -20 plus 60. -20 plus 60 is 40. Oh, look at that. It's curving back down, which makes sense because that's what an object in motion will do. When you throw it, it will go up and then gravity is going to take it back down, right? Okay. So now t equals 3. So instead of -5 times t squared is -5 times 3 squared plus 10 times 3. -5 times 9 now because 3 times 3 is 9. 10 times 3 is 30. -45 plus 70. So I'm really subtracting that. So it's 25. Yes. Okay, so these numbers are getting smaller now because first it's increasing, then your object is decreasing. It's falling down in terms of the height, right? It's getting closer and closer to the ground. So its height is going to go down relative to the ground. All right, and then last up, my number is 4 for t. 4 times 4 is 16. This is 40. 5 times 16, or -5 times 16 is -80. Plus 40 plus 40 is 80. Oh, okay, -80 plus 80 is 0. That makes sense because eventually this object, the stone, is going to hit the ground and then its height from the building, from the ground, actually, height from the ground, is going to be 0 because it is literally on the ground. So we want that. That just means its journey is over. It has fallen to the ground. All right, now we have our points and we're going to go ahead and plot them. But I do need to set up my axes first. So my x-axis was my t, my time. This time was in seconds, I believe. And then my y-axis was h, the height. Okay, and then it needs to go for time 0 to 4. So 1, 2, 3, 4, 5. For my height, it needs to go as high up as 45. 10, 20, 30, 40. Yeah, let's go by 5s. 10, 20, 30, 40, and 50. At 0 for time, the height was 40. So right there. After 1 second, it's 45. After 2 seconds, it's 40. After 3 seconds, it's 25. And after 4 seconds, it's 0. Okay, so now I can connect these, and I have, whoop, it's a little harder to make sure that it's accurate. But there's my quadratic. Okay, so there's my graph. Find the height of the building. Well, if we are throwing the stone from the building, then that's going to be my initial value, right? So the height of the building would be 40. And then the time of the flight of the stone. So how long the stone was up in the air. Well, it started at time 0, and it basically took 4 seconds to hit the ground. So it'd be 4 seconds. Okay. And then, let's see. Oh, and sorry, this was 40 meters. My bad. When is a stone 20 meters from the ground? Let me go ahead and fix my scale. This height is in meters. When was a stone 20 meters from the ground? Okay, this is meters, so 20 meters from the ground. It would have been about, I don't know, like 3.2 seconds. Yeah, 3.2 seconds. That's kind of an estimate according to the graph. And then state the line of symmetry of the graph in A. Okay, well, the line of symmetry is basically where it kind of turns back over, right? So if we were to continue this quadratic graph, it would look like this. So the line of symmetry is actually, let me put that in a different color. The line of symmetry will be right here. So this line of symmetry is where x equals 1. Okay, so after 1 second, that's when the stone kind of changes courses. Instead of going up in the air now, gravity's taking over, and it's then changing courses. The rate of change, instead of increasing, is now decreasing. Find the maximum height of the stone from the ground. Okay, well, at first the stone was at 40 meters from the ground because that's literally where it started at the height of the building. And then we threw it up. The highest point was right here between 40 and 50. So it was at the highest point 45 meters off from the ground. Oops, and then the only thing, I would want to change is I accidentally wrote x instead of t. So for this one, t equals 1 is the line of symmetry because we no longer used x, we used t for time. And that's it.